last video, we actually introduced ourselves to the concept of probability. We talked about the types of probability and we defined the key terms we can meet in probability, such as experiment, sample space, and event. So in today's video, we are going to be taking a more mathematical approach in studying probability. And in this video, we are going to be learning about the formula we can use to quantify the probability of an event. So I'm going to be assuming that I have an experiment, and this experiment of mine actually produced a sample space S. So I have my sample space to have just 4 events. This is me assuming. So the sample space of this experiment of mine is actually equals to A, B, C, and D, where A, B, C, and D are actually the events as a result of my experiment. So I need to get the probability that event A is actually going to occur. Now, the mathematical formula that defines the probability that event A will occur is denoted as P into bracket A. And mathematically, we have that P into bracket A is equals to the number of outcomes in this experiment of mine that favors event A divided by the total number of possible outcomes of this experiment. From our experiment, we can see that we only have just one outcome that favors event A, and we have a total possible outcome of 4. So that simply implies that the probability that event A is going to occur is equals to 1 divided by 4, which is equals to 0.25, which we can also say is 25%. This simply implies that whenever we have a probabilistic value of an event, we can decide to keep our answer in decimal format, or we can also decide to keep our answer in fraction. Anyone works fine. We also need to realize that the probabilistic value of an event can actually take a range of value, and this range of value is between 0 down to 100, including 0 and 100. So that simply implies that if we have the probabilistic value of an event to be equals to 0, it simply implies that there is actually no certainty. It is actually sure that that event is not going to occur. That is, it is sure, it is certain that that event is not going to happen. And when we have a probabilistic value that is equals to 100, it simply implies that we are 100% certain, or we are actually sure that that event is definitely going to happen. And if we have a probabilistic value that is actually equals to 50%, it simply implies that there is a 50% chance that this event is going to happen, and there is also a 50% chance that this event is not going to happen. And if we have a probabilistic value of 70%, it simply implies that there is a 70% chance, or there is a 0.7 chance that this event is going to happen, and there is a 30% chance that that event is not going to happen. So we can see a little pattern right here that if it is certain, or if there's a chance that an event is going to happen, definitely there is also a chance that that event is not going to happen. So if P of A represents the probability that event A is going to be occurring, so the probability that event A will not occur can be denoted as P into bracket A, then we have its complement. So P of A represents probability that event A will occur, and P complement of A represents the probability that event A will not occur. Mathematically, P of A plus P complement of A must be equals to 1. This is what we know as the complement rule in probability. Let us try to use more of a realistic example right here. So I'm going to assume the example of me rolling a die, a fair die, just once. The possible outcome of this experiment is actually going to be equals to 1, 2, 3, 4, 5, 6. And I can decide to ask you this question. So what is the probability that a 5 will show up? Now, the probability that a 5 will show up is actually going to be equals to the number of outcomes in this experiment that favors event 5 divided by the total number of outcomes that we have as a result of this experiment. That simply implies that how many 5 do we have divided by the total number of sample space. From this experiment, we can see that we only have just one 5. So that simply implies that the probability that a 5 is going to occur is going to be equals to 1 divided by 6. And if we take this answer to a decimal, we can see that we have our answer to be equals to 0.167. In the percentage, we have our answer to be equals to 16.7%. So that simply implies that there is a 16.7% chance that a 5 is going to show up when I roll a fair die. Let's try another number. What is the probability that a 3 is going to show up? And the probability that a 3 is going to show up is actually equals to the number of 3 we have in the experiment, which is equals to 1, divided by the total number of possible outcomes, which is equals to 6. And we have our answer to be also equals to 0.167. In fact, when you decide to roll a die just once, all of the events in the sample space of rolling a die just once have equal chance of showing up. We can also decide to tweak the question a bit and say what is the probability that an even number is going to show up. So the probability that an even number is going to show up is actually equals to the number of even numbers we have in the sample space divided by the total number of sample space. Now we have 3 even numbers right here, and that is 2, 4, and 6. So that means that the probability that an even number is going to show up is equals to 3 divided by 6, and that gives us 1/2, which is 50%. So that means that when we roll a die just once, there is a 50% chance that an even number is going to show up. It can be 2, it can be 4, it can be 6. We can also ask the question, what is the probability that an odd number is going to show up? And as you can see, we have 3 odd numbers also, and so the probability that an odd number will show up is equals to 3 divided by 6, and that gives us 1/2, 0.5, or 50%. So that simply implies that there is a 50% chance that an odd number is actually going to occur when we roll a fair die just once. So let's pick another example, and this time I will be using the example of tossing a coin just once. So when I decide to toss a coin just once, I have 2 outcomes, and that is equals to head and tail. So I can ask the question, what is the probability that a head is going to show up? As you can see, the probability that a head is going to show up is equals to the number of head that occurs from the sample space divided by the total number of sample space. We can see that we have just 1 head in the sample space, and we can see that we have a total number of 2 sample space. So that simply implies that the number of head is actually equals to 1 divided by 2, which is equals to 0.5, which is equals to 50%. So when we flip or toss a coin just once, we have a 50% chance of a head showing up. And what about the probability of getting a tail? We can also see that we have just 1 tail. So that means there's also a 50% chance that a tail is going to show up. One more example, and this time I'll be using the concept of a bag containing some balls, and then we decide to pick just a ball from the bag. So let's assume we have this bag that contains 7 red balls and it also contains 3 blue balls. So I decide to dip my hand into the bag and to pick just 1 ball at random. So what is the probability that that ball is going to be a red ball? And the probability of picking a red ball is actually going to be equal to the number of red balls we have in the bag divided by the total number of balls. So the total number of balls in the bag is actually equals to 10, and we have 7 red balls. So that simply implies that the probability of picking a red ball is actually going to be equals to 7 divided by 10, and that is 0.7. And the probability of picking a blue ball is going to be equals to the number of blue balls we have inside this bag divided by 10, and that's going to be equals to 3 divided by 10, and that gives us 0.3. So there's a 70% chance that if I dip my hand in the bag to pick a ball at random, I have a 70% chance of picking a red ball and a 30% chance of picking a blue ball. So let's talk about sample space and how complex our sample space can get when we decide to perform our experiments several number of times. So let's start with the idea of us rolling a fair die just once. And if we decide to roll a fair die just once, the sample space of such experiments is going to be equals to 1, 2, 3, 4, 5, 6. Now let's assume we decide to roll 2 fair die at the same time. So what is going to be the sample space, or what does the sample space look like? And this is what our sample space looks like. If you take a closer look, you can see that we have a total possible outcome of 36. Now let's assume we want to roll 3 fair die at the same time. What does the outcome look like? And this is what the outcome look like. And if you decide to count this, you can see that we have a total of 216 possible outcome when we decide to roll 3 fair die at the same time. You can notice a pattern here, and that is when you increase the number of times the experiment was performed, in this case probably increasing from 3 die to 4 to 5 to 6 to 7, you would notice that the sample space actually gets wider or we can say the sample space gets larger and grows exponentially. It becomes more complex for us to be able to extract the sample space of such experiments. Let's take another simple example. In this case of ours, let's decide to talk about the tossing of a coin. So if we decide to toss a coin just once, we have the outcome to be equals to just head and tail. If we decide to toss 2 coins at the same time, we can see that the possible outcomes is going to be head head, we have a head tail, we have tail head, and then we have tail tail. Now let's assume we want to now toss 3 coins at the same time. What does the sample space looks like? We can have something of this nature. As we can see, when we toss our coin just once, we have just 2 outcomes, and when we toss 2 coins, we have 4 outcomes. When we toss 3 coins, we have 8 outcomes. If we toss 4 coins, we are going to be having 16 outcomes. As you can see, the sample space is actually growing exponentially. Now ask yourself, what do you think the sample space is going to be when we have like 50 coins tossed at the same time? It's actually going to be a very large one. And how do you answer a question that talks about experiments performed in a large number of times? And this is where you have to think of other ways to extract out the sample space of experiments like this so that you can calculate the needed probability. And one of the tools we use when we try to get to situations where we perform our experiments a large number of times is the concept of permutation and combination, which we are going to be learning in later videos. In our next video, we talk about the type of events where we discuss things like the mutually exclusive events, the mutually inclusive events, dependent events, and independent events. If you learned something new, I would really appreciate if you can like this video and subscribe to this YouTube channel. Turn on your notifications to get notified when I release new video. Thanks for making it to the end of this video, and we see you in the next one. Bye for now.